In this video, I just quickly want to go over some infinite limits using non-algebraic functions. I'll get right down to an example. So the example is x over 1 plus cosine of x, and we're looking at the limit as x goes to pi, let's say for the right, from the right for the time being. Now if we just plug in, because this is an example of a function you should be able to plug into as long as everything goes well, we get pi over 1 minus 1, which is pi over 0. Okay, so this signals an infinite limit. And so the question becomes, is it a plus or minus infinity? Now, following what we've done previously, we take a look at the numerator, that's going to pi, and the denominator, and that's going to 0. Right, so this denominator is what we have to figure out. We have to figure out the sign of this 0, positive or negative. And when we were dealing with algebraic functions, in order to do that, we looked at this limit here, which tells us that x is bigger than pi, right? And that would have told us that x minus pi is greater than 0, or equivalently that pi minus x is less than 0, just by subtracting pi from both sides or subtracting x from both sides. But in this case, we have a non-algebraic function. Right, so like in previous examples, we'd have a polynomial where x minus pi or pi minus x would be a factor of this denominator, but this is not a factor of this denominator because we don't have an algebraic function. So we have to do something different here. And basically what we have to do, it just comes down to, we have to know what we're dealing with. We have to understand this function, in particular this denominator that's going to 0, the 1 plus cosine of x. So we need to understand this 1 plus cosine of x better. That's going to get to the root of the problem. And the easiest way to see what's going on is just look at the graph. So let me produce the graph of 1 plus cosine of x for you. So here's the graph of cosine in red here, the familiar up and down profile, right? And then 1 plus cosine of x is just shifting that up 1. Right? So we have that same profile, but just shifted up vertically by 1. And so that shift upward by 1, that means that, so usually cosine goes from a peak of 1 to a trough of negative 1, right? Peak 1, trough negative 1, back up to 1, back down to negative 1. That shift up from 1 means it has a peak at 2 and now a trough at 0. And so the x values corresponding there are 0 and pi. So it's 0, it's at 2 at its peak, and then in the bottom of this valley at pi. Right? So you have this now going from 2 to 0 every pi, sort of switching between peak and valley every pi. And so you can see directly from the graph that as x approaches pi, we're approaching 0, right? And no matter what the x value is, our output value of 1 plus cosine is positive, or at least non-negative. Right? We only hit 0 at these certain multiples of pi here. And so what we immediately conclude from the graph is that 1 plus cosine of x is positive. And so we get this positive here from the graph. And so that leads us to conclude that combining the positive here, the pi, which is positive up here, that we have a positive infinity as our limit. And in fact, you can see it doesn't matter whether we approach from the right or the left here. So really, we can just talk about the limit as x goes to pi. Right? We get infinity either way, because the sign of 1 plus cosine of x is positive to the left and the right of pi. And one way we can go about doing this without the graph, if you maybe you want to think about this a more sophisticated way without having to draw out the graph. Instead of using the inequality that x is greater than pi that we got from the, well, when we were talking about the right-handed limit, right? So back when we were talking about algebraic functions, we would sort of try to take the handed limits and get inequalities like this. Well, there's a different inequality that we can work with here, and that comes directly from the function. So a fundamental fact about cosine is that cosine of x is between 1 and negative 1. Okay, so this is a fundamental thing you want to keep in mind. And this is true also of sine. And so what we get directly from this inequality, right, we have our cosine here cosine here, I want 1 plus cosine, so I'll just add 1 to everything in this inequality. So I get 1 plus cosine of x is less than or equal to 2 and greater than or equal to 0, just adding 1 to each of the things in that inequality. And so what I'm interested in here is this part of the inequality. We find out that, right, because we're interested in this sign of this quantity. So we find out that no matter what x is, 1 plus x is greater than or equal to 0. So that tells us the sign. And this is exactly what we found out from the picture, but we can get it directly from this well-known inequality about cosine of x. So you can use the graph if you want to think about these inequalities, or you can just go directly to the inequality. So the last example I want to discuss regarding infinite limits with non-algebraic functions is natural logarithms. So we have a natural logarithm base b here. We'll consider b greater than 1, most common case. So you think about b equals, say, 2, or e, which is the natural logarithm, or 10, being the most common bases there. And the graph of this function is rather familiar. It looks like this. So that's the graph, which should look familiar. And the point here on the graph is at x equals 1. So x equals 1, y equals 0. And there's a rather obvious feature of the graph, which is this vertical asymptote as you approach 0 from the right. So this function has a domain from 0 to infinity, open interval 0 to infinity, and the limit as you approach that 0, as x approaches 0 from the right, of log base b of x is equal to negative infinity. Okay, so we see an infinite limit for this non-algebraic function here. Now, an interesting variation on this to discuss is if we take log base b and we insert a polynomial inside of this logarithm function. And in this case, we'll have vertical asymptotes. We'll have infinite limits wherever p of x equals 0. Okay, so if you have p of x equals 0, then that's sort of plugging 0 into this log. And log at 0, right, that's where the vertical asymptote is. So whatever x values give p of x equal to 0 is going to end up being a vertical asymptote of log base b. As a concrete example, we can consider the following. Log base 2 of 2 minus x. So simple polynomial, just linear polynomial on the inside of the log there. So we'll think about this in a simple way, just graphically. So the graph of this function is related to log base 2. We can figure out the graph easily enough just from the graph, the familiar graph profile that you see up here. And the way that works is we can think about this log base 2 of 2 minus x as a transformation of the graph of log base 2 of x. So you can think of this in stages, starting with log base 2 of x. Right, we first add 2, so we have 2 plus x here. And this is a leftward shift by 2. Okay, so it's a little bit counterintuitive. Adding 2 inside to the x there is going to be a shift to the left by 2. And the next step would be to negate this x here. So if you negate the x, what that is going to be a flip of the graph around the y-axis. Okay, and so I'll show you what that looks like visually in stages. Okay, so here's what it looks like. We start with the graph of log base 2 of x. We shift that to the left by 2. So this vertical asymptote at 0 is now at negative 2. This point at 1 is now at negative 1. And then we flip this over the y-axis. So the negative 2 asymptote flips to 2. Negative 1 here flips to 1. And we arrive at the graph of log base 2 of 2 minus x. And so from this, you can see we clearly have a vertical asymptote at x equals 2, and the limit as we approach from the left to 2 is equal to negative infinity. And so I've summarized the information that we've determined here. So in this example, Since this polynomial here vanishes at 2, we knew we were going to have a vertical asymptote at x equals 2. That was the easy part. What all the graphing was for is to figure out what the associated limit was, right? So we had to figure out, how is the graph approaching this asymptote? And it turns out the graph is approaching it from the left. So generally speaking, when you have this log with a polynomial inside type of situation, what you want to sort of understand is what the domain of this function is, because knowing the domain of the function is going to tell you how the graph approaches the asymptotes. And to determine the domain of a log composition function, you need to know where the function on the inside, in this case our 2 minus x, is greater than 0, because log only accepts positive inputs. Right? So in this case we had to know where 2 minus x is greater than 0. Of course that's where x is less than 2. Right? So since x is less than 2, and we know that at 2 we hit 0, that's going to tell us that we must be making an approach to 2 from the left. So I can illustrate this with a slightly more complicated example. So if we consider log base 10 of x squared minus 1, if we want to know the domain of this function, we just have to know where x squared minus 1 is greater than 0. So the domain is where x squared minus 1 is greater than 0, and from a simple graph of x squared minus 1, we see that's where x is bigger than 1, where x is less than negative 1. And then we have our asymptotes where the x squared minus 1 equals 0, so where we're plugging 0 into the log. And that occurs where x is 1 and where x is negative 1. So you can easily graph the domain of this function. So the domain of the function is all the stuff in green, to the right of x equals 1, to the left of x equals negative 1, and those vertical lines, x equals 1 and x equals negative 1, are the vertical asymptotes. So our function has to look like, something like this. And this is just a little piece of it, but it's got to be going to negative infinity as we approach 1 from the right and negative 1 from the left. So we have a limit as x approaches 1 from the right of log base 10 of x squared minus 1 equals negative infinity, because the infinite limit associated with log is always negative infinity. And then we have the limit as we approach negative 1 from the left of log base 10 of x squared minus 1 equals negative infinity. So with the log, the negative infinity, that's the easy part to figure out. The more interesting thing is figuring out how you make the approach to the appropriate point. Right? So this 1 you get from where does this thing inside the log, where does that equal 0? And then to determine how the approach is being made, you need to look at the domain. So you need to look and see where the inside function, the polynomial inside the log, is greater than 0. Okay, that's all for now.